Welcome to lecture number 74. We are studying transient analysis, and in our last lecture, CA73, we studied an expression for the current in a series RC circuit, which contains a switch K, and the K switch was closed at time t is equal to 0. And we studied that just after it was closed, the capacitor was replaced with a short circuit at time t is equal to 0, and IC of 0 was V over R because C was replaced with a short circuit, V over R. Then the voltage drop across capacitor, it starts building up and the current decreases, and it decreases exponentially, and at time t is equal to infinity, it becomes 0. This is what we studied in our last lecture, and using differential equation approach, we solved a first order linear equation and we computed an expression for IC of t for all values of t. So now this is our general expression. We can put any value of t in this equation and we can find IC of t. So we can use any program like MS Excel or MATLAB to plot this expression, right? So we can plot it by using any programming tool, but we can plot it using some work we can do manually, but that won't be enough because we can compute IC at different values of t, but computing IC for all possible values of t will be difficult. So therefore we'll prefer using a computing tool. So for now, we just check what is IC at time t is equal to 0. It comes out to be V over R. And IC at for very large value of t, after a very long time, IC at infinity, it comes out to be equal to 0. And for all these middle values of t, you can put any value of t, maybe IC of 0, IC of 1, 2, but that will take a lot of work. So it's better we use a computing tool like MS Excel or MATLAB, which I will try to use in our upcoming lectures. Right. So in this lecture, we will study what is the voltage drop across this resistor. Once we know the current flowing this series circuit, finding voltage drop across R is straightforward. Just we have to multiply this current with the value R, the value of resistance. So it's pretty straightforward. Finding this VR of t is simple. Just multiply IC of t by R, the value of the resistance. So this R cancels with this R and we are left with V e to the minus t over RC. This is also the same exponential, but this is the same exponential, but VR of 0 would be V, right? So for time t is equal to 0, the value comes out to be V, whereas for IC of t, it comes out to be V over R. So this value is different, right? But the important thing is that this IR of t and IC of t and VR of t, they both have the same shape. They have to, because VR of t should have the same shape as IC of t, because we obtain VR of t by multiplying IC of t with a scalar, a constant term R. So they have to have the same shape. So they have the same shape, right? And the final thing that we have to compute in this lecture is the voltage drop across this capacitor for all t. So it acts like a short circuit just after we have closed the switch, but not always. So we have to compute this voltage V sub C of t, the voltage drop across t, a general expression, a quite general expression for the voltage. And if you put t is equal to 0 in that value, in that expression, it should come out to be 0 because initially the voltage drop across it is 0. So let's see how can we compute it. Right, this is the formula we studied a couple of lectures before. Vc of t is 1 over c integral from minus infinity to t, and we have to integrate ic of t. This is the formula that we already know, and we know the expression for ic of t we studied in last lecture. So what we have to do is we have to just plug in this. We have to just plug this ic of t here. This ic of t, let's plug it here. So what happens is then ic of t is minus infinity to t, and we can plug, we can rewrite this integral minus infinity to t. We can, in fact, we can break this up into two parts, from minus infinity to 0 and from 0 to t. From minus infinity to 0 if it is non-zero if the capacitor is pre-charged, but in this case, since the switch was open before time t is equal to 0, so the capacitor was uncharged. There was no initial charge on the capacitor. Therefore this term is 0. It's not charged. It's not already charged. So we are left with this term. The range of the integral is from 0 to t. So now plug the value of ic of t that we computed in last lecture, v over r e to the minus t over rc, and this v over r is a constant. We can take it outside of the integral, v over rc, and then we compute this, the integral for this exponential term. Minus 1 over rc should be written in should be written in the denominator, and the same integral, we write the same integral once again. This integral, this type of integration was studied by us in elementary classes. It's a very simple integral for exponentials, and this denominator of denominator is actually numerator, so we bring it in numerator. This rc cancels with this rc, and then we put the limits, e to the minus t over rc, and then 0. We put the second limit 0. So e to the minus 0, we already know what is e to the minus 0. E to the minus 0 over rc is actually e to the minus 0. It can also be written as 1 over e to the 0. 1 over e to the 0. Anything raised to the 0 is a 1. So 1 over anything raised to the power 0 is a 1. So 1 over 1 is a 1. So e to the minus 0 over rc is actually a 1. So we replace it with a 1, and there is minus v outside. So if we multiply this minus inside, this minus becomes plus, this plus becomes minus. So vc of t is v e to the minus t over rc. This is the expression, a general expression for Vc of t for all t, including t is equal to 0 and t is equal to infinity. So let's check this expression before we plot Vc of t. Before we plot it, let's check this expression. Vc of 0. Let's try to calculate Vc of 0 for time t is equal to 0. This is 1 minus e to the minus, put this t is equal to 0, 0 over rc. So 1 minus, when we know this e to the minus 0 is a 1, so it comes out to be 0 volts. This is what we studied in last lecture and even in CA72, that initial value of Vc, the capacitor voltage drop across capacitor, is 0. It acts like a short circuit. At time t is equal to 0, it acts like a short circuit. If it is a short circuit, the voltage drop across it at time t is equal to 0 should be 0, and it is. Now we have proved it mathematically that it is 0 volts. At time t is equal to 0, the voltage drop across capacitor is 0. And what happens to the voltage drop across it for time t is equal to infinity? This is v times 1 minus e to the minus infinity. Instead of this t, we put up an infinity, and e to the minus infinity is a 0. How? e to the minus infinity is 1 over e to the infinity, and anything raised to the power infinity is an infinity. So this is 1 over infinity, and 1 over infinity is a 0. So therefore e to the minus infinity is a 0. So it comes out to be V. So after a very long time, the capacitor charges to a value equal to the supplied voltage. So this is Vc of t plotted versus t. Initially it is 0, and then the voltage across capacitor starts building up slowly and becomes equal to the supply voltage as the time approaches infinity. Right. This is all for this lecture. We have studied expressions for IC of t, V across R of t, V across C, V across capacitor as a function of time. And we have also learned how to write KVL equation for this circuit, for this transient circuit. And we have also learned how to solve that differential equation to find out the solution for the unknown variable. In our upcoming lectures, we'll solve more examples of transient analysis involving resistors, capacitors, and inductors. Thank you.